I thank the organizers for their kind invitation to speak at this joyous occasion. I met Gopal Prasad for the first time in 2008. I was a graduate student and I came to the University of Michigan to give a talk at the seminar. And after the talk, on the way to dinner, Gopal, with just a few polite questions, brought me to the brink of my understanding and showed me how much more I had to learn about my subject. 2 years later, a friend of mine and I decided to work on a project that was just a bit outside of our areas of expertise. It concerned the asymptotic questions in the geometric group theory of arithmetic groups. And the two of us made little progress in this until we participated at a conference at the University of Virginia, and we were able to speak with Gopal. Over the course of one lunch discussion, he propelled our project and we were able to complete it soon after. And if there was any doubt that this may have been just a lucky coincidence, my friend and I repeated this experiment 2 years ago, and the results were exactly the same. Since I came to the University of Michigan, I've been able to discuss with Gopal regularly, and I have found him to be an incredible source of inspiration and knowledge. I've learned much mathematics from him, and I've also learned from him and his wonderful wife, Indu, a lot about life in general. So it is a great pleasure and a true honor for me to be able to celebrate with you today his mathematical achievements. He has had a profound influence on many different areas of mathematics, but I'll discuss the one area that I feel most comfortable with, which is the representation theory of p-adic groups. I will want to begin with a motivation and an overview of that area, after which I will discuss Gopal Prasad's fundamental contributions, as well as the results of other people who have been influenced strongly by both his results and his methods and ideas. Let me begin by reminding you of a basic principle in algebraic number theory, which is called the local to global principle. And what this principle is the following. Imagine that you have a problem of arithmetic nature for the field of rational numbers. For example, you may be interested in solving a polynomial equation. One thing you could do is consider the same problem over the real numbers. The real numbers have much simpler arithmetic, so solving this problem will be much easier. And it's clear that if you cannot solve this problem over the real numbers, then you will not be able to solve it over the rational numbers. But the information that the real numbers provide is fairly limited. So what could do is augment this information by considering not only the real numbers, but also the p-adic numbers. The p-adic numbers are a cousin of real numbers. They share very similar features with the real numbers, but they also have differences. The arithmetic of the p-adic numbers is simpler than the arithmetic of Q. It is more complicated than the arithmetic of real numbers. And the idea is that if you're able to solve the global problem, which is the problem over Q, if you're able to solve it over the real numbers and over the p-adic numbers, then that may not be sufficient. It is sometimes sufficient, but rarely, to solve the problem over the rational numbers. But even if it is not sufficient, it provides a great deal of information and help towards solving the problem over the rational numbers. So in a few words, what are the p-adic numbers and how similar or different are they from the real numbers? Well, the p-adic numbers are obtained just like the real numbers from the rational numbers by a process of completion. The real numbers are the completion of the rational numbers with respect to the Euclidean metric. The p-adic numbers are the completion of the rational numbers with respect to a different kind of metric of a more arithmetic nature, where two numbers are considered close if the difference is very divisible by the prime number p that we have chosen for the p-adic numbers. Because of that, both the real and the p-adic numbers are topological fields, and the topology is complete and also locally compact in both cases. And what this allows is we have a robust theory of analysis that we can use. So we have integration on these fields. we have the concepts of convergence, we have Fourier transform, and so forth. So we can perform harmonic analysis on these fields. On the other hand, those two fields are actually quite different from each other. For example, the topology of R is connected and even locally path connected. So it has strong connectedness properties. On the other hand, the topology of the p-adic numbers is totally disconnected. There are also differences in the way the integers sit as a subring of the real and p-adic numbers. In the real numbers, the integers are discrete. In the p-adic numbers, this is not true, and we can take the closure of the integers in the p-adic numbers, and what we obtain is a subring which is compact and open and is called the ring of p-adic integers. Now, with the emergence of the theory of automorphic forms and the Langlands conjectures, the local to global principle has been given new clothes, and from that vantage point, it is the principle of studying the representation theory and the structure theory of groups of the form GR or GQP, where G is some reductive p-adic group, some connected reductive algebraic group. This is so because in modern language, an automorphic form, f, which is classically a function, is considered an element of a so-called automorphic representation, and the automorphic representation itself is a tensor product of representations pi p, and each of these pi p's is a representation of a GQP or of a G of R. So to study an automorphic representation, or its elements which are automorphic forms, part of it is to study the local problem, that is to understand these local representations. So before I continue, I'd like to say a few words about reductive groups, because they play a central role here. So what is a reductive group? The basic examples of reductive groups are the so-called matrix groups. For example, we can consider the group GLN of n by n invertible matrices. Or we can impose some additional linear algebraic structure, like considering the group of n by n invertible matrices that leave invariant a certain fixed symmetric bilinear form. There are other linear algebraic structures that one can impose, for example, symplectic forms, Hermitian forms, and so forth. And the concept of a reductive group is a kind of a very vast generalization of this linear algebraic phenomenon, and gives one language to speak about all these different kinds of groups that may arise in this way, or maybe even more abstractly. For me, the go-to example for this talk is going to be the group SL2. So these are 2 by 2 invertible matrices. With determinant 1. Now, such matrices can be taken with entries in pretty much any field or ring that one is interested in. For us, we'll be interested in the fields of real or p-adic numbers or the ring of p-adic integers. And when we do so, what we obtain is not just an abstract group, say SO2R or maybe SO2QP, but in fact the topology of the underlying field gives a topology on the group as well and makes it into a topological group. And again, there are some common aspects of the topologies and the group theory, and then there are some differences. The common aspects are that both of these groups are locally compact topological groups. And again, this introduces into a theory, a very good theory of analysis, for example, integration, Fourier transform, convergence, and so forth. At the same time, the topologies are again quite different. This topology here is connected and locally path connected. The topology here is totally disconnected. Another difference, which may be seen maybe as a difference in the group theory, is that the group SO2R has a unique maximal compact subgroup. And that, when I say unique, I mean unique up to conjugation within SO2R. And that maximal compact subgroup is the group of 2x2 rotational matrices, which is the same as the circle group. On the other hand, SO2QP has two distinct maximal compact subgroups. One of them is the group SO2ZP, 2x2 invertible matrices with determinant 1, where the entries are in the ring of p-adic integers. And the other one does not have a name like this, but we can write it by specifying its entries. The diagonal entries will be in the ring ZP, but the off-diagonal entries will be pushed by P. So the upper one is multiplied by P inverse, the lower one is multiplied by P. As you can see, the unique maximal compact subgroup is actually abelian in SO2R, whereas the two maximal compact subgroups in SO2QP are non-abelian. Another difference in the group theory is that there is essentially no subgroup of the compact subgroup of SO2R that has the same kind of topology. For example, we could say that there is no non-trivial Lie subgroup of SO2, or maybe no non-trivial connected subgroup of SO2. On the other hand, on the side of SO2QP, if we consider subgroups of SO2ZP that has the same kind of topology, it turns out that there are infinitely many such. One obtains them by placing congruence conditions on the entries. And this will be an important observation for us to discuss later. Now that we have understood a little bit about what these groups look like, let us talk about representations. So a representation of such a group, so let me now use the symbol G to denote either SO2R or SO2QP. So a representation of G is going to be a linear action of G on a complex vector space V. There has to be some continuity property that I'm not going to specify precisely, which takes into account the topology of the vector space V, as well as the topology on the group G. And it is most often the case that the dimension of V is going to be infinite. In fact, the group SO2R has finite dimensional representations, and they do play some role in the theory, although it's not a major role. And the group SO2QP turns out to not have any finite dimensional representations besides the trivial representation. So in lieu of the finite dimensionality, Harish has introduced the concept of admissibility in order to get a handle on these representations. So what is an admissible representation? Well, it has to do with the maximal compact subgroups that the group G has. So if we take a maximal compact subgroup and restrict the representation to this maximal compact subgroup, admissibility requires that the result is a direct sum of irreducible representations. And the key requirement is that each irreducible representation comes with finite multiplicity. So because of the dimension of V is infinite, and each irreducible representation of K is finite dimensional, there will be infinitely many irreducible representations that contribute to this direct sum, but each of them is allowed to only contribute a finite multiplicity. And so the goal of the representation theory, or one of the main goals, then becomes the classification of irreducible admissible representations. The reason admissibility is a good condition is because it is enough to study all the unitary representations, and in particular, all the representations that occur as local components of automorphic representations, namely the pi piece that we saw up here. And in order to get a handle on the classification of admissible representations, Harish introduced two important subclasses, namely the square integrable and the temperate representations. To explain what these are, let me remind you of the concept of a matrix coefficient. So if we're in the simple setting where we have a finite dimensional representation, we can choose a basis of this representation, and then it becomes simply a group homomorphism into the group of n by n invertible matrices with complex coefficients. And then, if we specify a pair of indices I and j, what we can do is we can consider the ijth entry of the matrix which is associated to any element of the group G. And in this way, we're going to obtain a function, let's call it mij for matrix. And it is a complex valued function on the group, which associates to each element G of the group the ijth entry of the matrix that this representation associates to it. And using basic linear algebra, we can express this function by an explicit formula that looks like this. We take the jth standard basis vector of C to the n, we move it by the matrix G, and then we pair this with the ith dual vector. So here E1 to En is the standard basis of C to the n. And the same kind of construction works even when we have an infinite dimensional representation. So now G is going to act on some complex vector space V, which may be finite, but it's usually infinite dimensional. And what we do is we take just an arbitrary vector in V and an arbitrary vector in the dual, and we form the function mv lambda, which sends an element G to exactly the same kind of pairing. And we call this a matrix coefficient. So for any V and any lambda, we have the matrix coefficient function. And Harish-Chandra's definitions are that a representation V, or pi V, is square integrable if all of these matrix coefficients are in fact square integrable functions on the group. Remember that because the group is a locally compact topological group, there is a good theory of integration on it. Now this is the definition when the center of the group is finite, which is the case in our example of SO2. In general, we have to divide out by the center, but then the definition is the same. The definition of a representation being tempered is very analogous. Here we require that the matrix coefficient, well, it cannot be square integrable, but it should almost be square integrable. So it should be p integrable for any p bigger than 2. So this gives us a classes of representations. So the tempered representations are a certain subclass of the admissible representations. And the square integral representations are an even smaller subclass here. And the way these subclasses function in the classification of the admissible representations is via a device called parabolic induction introduced by Harish-Chandra, which produces representations of G from representations of smaller subgroups of G, which are called Levy subgroups. Using this device, it's a fundamental result of Langlands, called the Langlands classification, that any irreducible admissible representation of G is obtained by parabolic induction from a tempered representation of a Levy subgroup of G. And this result is so precise that it reduces many questions about irreducible admissible representations to questions about tempered representations. And there is a similar phenomenon in the step between tempered and discrete. This is called the Harish-Chandra theory of the R group. Again, it states that one can obtain any tempered representation via parabolic induction from a square integral representation. This classification result is slightly less well understood, and there's still some open questions about it, both of analytic and algebraic nature, but roughly we understand fairly well how to relate tempered representations to square integrable representations. What these two results show us are two interesting phenomena. The first obvious phenomenon is that square integrable representations become an essential focal point of the theory. If we understand square integrable representations, then these results reduce questions about the other kinds of representations, the more general admissible representations, to those. Now, what is known about square integrable representations? So over R, that is, if our group G is the R points of a connected reductive group, the square integral representations were completely classified by Harish Chandra. So I will say more about this classification a little bit later, but for now I can give you a simple example. For the group SO2, the square integrable representations are classified by non-zero integers. And when the integer is positive, one can realize a discrete series. I'll probably keep saying discrete series representation, which is synonymous with square integrable. They can be realized in certain functions on the upper half space, and they're closely related to cuspidal modular forms of weight k plus 1. On the other hand, over the p-adic numbers, this is in general still an open problem. In the previous decades, a lot of information and a lot of progress has been made on this open problem, and this will be one of the main topics of this talk. Now, a second phenomenon that is visible in these results of Langens and Harish Chandra is, at first point, maybe a little striking. And it is the fact that even though the topological structure, as well as the group structure of real and p-adic groups, is so different from each other, the representation theory in both cases seem to behave in an analogous way. Both the Langens classification and Harish Chandra's theory of the R group work equally well for real reductive and p-adic reductive groups. And this has become known as the Harish Chandra Lefschetz principle. It is the philosophy that real and p-adic groups ought to behave in similar ways despite their differences. So now that I've given a rough outline of representation theory of real and p-adic groups, I can begin discussing Gopal Prasad's fundamental contributions to that theory. And the first result that I would like to focus on is called the Moy-Prasad filtration. So Prasad's results actually begin at the opposite end of where the Lefschetz principle is situated. They begin with embracing the particular nature of p-adic groups and those parts of it especially that makes them different from real groups. So let me give you a few examples. Consider the maximal compact subgroup SO2ZP of the p-adic group SO2QP. We can write it somewhat symbolically by indicating that the 4 entries are inside of the ring of p-adic integers. And we can start placing congruence conditions on these entries to obtain smaller and smaller groups. So on the diagonal, I'm going to place multiplicative congruence conditions, whereas off the diagonal, I will place additive congruence conditions. And by increasing the power of P, we'll obtain smaller and smaller subgroups. So this filtration is indexed by integers. This is the 0th piece, this is the first, this is the second piece. And the filtration index tells us what power of P we're putting as a congruence condition. Now, this can be done for any maximal compact open subgroup of SO2ZP, and it always works in the same way. In fact, the open compact subgroups of ZP are organized by a geometric structure that is a p+1 regular tree. So let me draw the example where p is equal to 2. So it's a 3 regular tree. And because it's an infinite tree, I'll have to stop drawing at some point. And maybe this some point is now. And the 2 compact open subgroups that I have talked about so far are associated to these 2 vertices. So here we'll have SO2ZP, and here we're going to have the other one that I mentioned above, where the top right entry is multiplied by p-1 and the bottom left entry is multiplied by p. But there are also compact open subgroups associated to the edges in that tree, and those are very important. They're called the Iwahori subgroups. So here, the Iwahori subgroup looks like this. And one can say it is obtained by intersecting the two compact open subgroups that correspond to the two vertices of this edge. But one can define what an Iwahori subgroup is in a different way too. It is the normalizer of a maximal pro-P subgroup. And the equivalence of those two definitions is not obvious, it's part of what is called Brouhat-Titz theory. Now, the Iwahori subgroup also has a filtration associated to it, but this filtration behaves a little bit differently. First of all, it is indexed not by integers, but by half integers. So this is the zeroth piece. In the 1/2 piece, only the diagonal entries change, and the off-diagonal entries stay the same. This is the piece at 1/2. Whereas at the next step, the diagonal entries stay unchanged, and the off-diagonal entries change. This is the piece at 1. And these are examples of Moy-Prasad filtrations. So what happens generally, so for a more general connector to reductive group, there is a polysimplicial complex that we're going to denote by B of G, called the Brouhat-Titz tree, the Brouhat-Titz building, which is a tree in the case of SL2, so it's a simplicial complex of rank 2 or dimension 1. But more generally, it will be a polysimplicial complex of a rank depending on the group G. Its vertices, which are the zero-dimensional polysimplices, are going to correspond to maximal parahoric subgroups. These are closely related to maximal compact subgroups, as in the case of SO2, but in general, they may be slightly different. Whereas on the other extreme, namely the polysimplices of largest possible dimension, these are called chambers, they're going to correspond to Iwahori subgroups. And what Moy and Prasad do, and in fact, this was already done in some form in an earlier work of Gopal Prasad with Raghunathan on topological central extensions, but it was used in the representation theory of these groups by Moy and Prasad. What they do is they associate to any polysimplex in the Brouhat-Titz building a filtration of the corresponding parahoric subgroup. And this is a separated filtration, which means that it converges to the trivial subgroup, and it is a filtration by compact open subgroups. And another very important feature of these filtrations is something that we can already observe in these examples, namely, let us consider consecutive quotients in this filtration. So in the first filtration, the quotient of the first step is the group SO2FP. So now we've used yet another field in our reductive group SO2. This is the finite field with p elements, which happens to be the residue field of the ring of p-adic integers. And the quotient in the second filtration step turns out to be the Lie algebra of SO2 evaluated at Fp. And something similar happens with the filtration of the Iwahori subgroup, where in the first step, the quotient is Fp cross times Fp cross, whereas in the second step, the quotient is Fp direct sum Fp. And this has become known more generally as the Moy-Prasad isomorphism. And what the Moy-Prasad isomorphism is, it is an isomorphism between consecutive quotients in the Moy-Prasad filtration for the group and corresponding consecutive quotients in the Moy-Prasad filtration for the Lie algebra. So this allows passage between the group and the Lie algebra. And both the filtration and the isomorphism have become an indispensable tool in the study of both the structure and the representation theory of p-adic groups since they were introduced. But before returning to representation theory and explaining to you how these tools are used, I would like to introduce another fundamental result of Gopal Prasad, and that concerns actions of finite groups on buildings. So this was a result that is obtained in collaboration with Zhu Yu and begins with the following observation. So when you study p-adic groups, it is a useful technique to be able to extend scalars from the p-adic numbers to some finite extension, often a Galois extension. So let us consider a finite Galois extension of QP with Galois group gamma. Of course, the same technique is useful over the real numbers as well, except there are not all that many finite Galois extensions of the real numbers. Whereas the arithmetic of the p-adic numbers is much richer, and in particular, there are infinitely many finite Galois extensions. There are finite Galois extensions of arbitrary degree, and even if the degree is fixed, there are different kinds of finite Galois extensions of that degree that have different properties regarding ramification, for example. So what one may be interested in is to compare the Bruhatid's building of the group G over QP with the Bruhatid's building of the group G over the extension field E. The building is a natural object, so the Galois group is going to act on it, and we're going to expect some relationship between the Galois fixed points in the building over the larger field with the building over the smaller field. And it is clear that there is going to be an embedding, but one would like to say something more. One would like to say that this embedding is actually an isomorphism, which will be a statement of the type of Galois theory. And it is a theorem due to Rousseau and later also Prasad that this is indeed the case, provided the extension is tamely ramified. So under the assumption that E over QP is a tamely ramified extension, the building of G over QP is equal to the Galois fixed points in the building of G over E. So this was proved in Guy Rousseau's thesis, and it was embedded in a kind of lengthy and complicated study of the building of G over E without assuming that E over QP is tamely ramified. And what Prasad was able to do is he was able to find a completely different and very geometric and beautiful argument that only took a couple of pages and got right to the point of why this equality is true. And later Prasad was able to use these ideas in his collaboration with you to prove a much more general theorem, which states the following. Assume now that you have a finite group gamma. It doesn't have to be a Galois group. And it is such that P does not divide its order. This is a replacement for the assumption that E over QP is tamely ramified. And this finite group, we're going to let it operate on the reductive group G. Then the statement is that, first of all, the group of fixed points, let's take its connected component, this is reductive. And moreover, the building of this reductive group is equal to the building of G gamma fixed points. So this is a vast generalization of the previous result. And the way the previous result can be reduced is by using a technique called Weil restriction of scalars. Let me give you one particular example of an application of these kinds of results to the structure theory of p-adic groups. It is the so-called canonical point introduced by Prasad. And it is in the following situation. One considers an anisotropic maximal torus in the case of SL2, an anisotropic maximal torus would be given by a quadratic extension of QP, and it would be, in fact, equal to the norm 1 elements in that quadratic extension. So if P is not 2, they're going to be up to isomorphism 3 different such tori, 1 for the unramified quadratic extension and 2 for the 2 different tamely ramified quadratic extensions. In that case, what we can do is we can consider the building of G over a tamely ramified extension that splits this torus, and we can consider the building of that torus as well over this extension. There is a canonical embedding of the building of the torus as a so-called apartment into the building of G. And this embedding is Galois invariant, so we obtain an embedding on Galois fixed points. Now, on the one hand, because of the assumption that the torus is anisotropic, there is a unique Galois fixed point in its building. And on the other hand, by the result that we just introduced, the Galois fixed points here are just the building of G over QP. And the image of this point in the building of G over QP is the canonical point of this anisotropic maximal torus. In the example of SO2, where we had the tree, although now I have to draw a tree for P that is not equal to 2 in order to accommodate for a tame ramification. Then the unramified maximal tori, they're going to sit here on the vertices. So these are canonical points that occur for unramified maximal tori, whereas the ramified maximal tori, they're going to be associated with barycenters of edges. I've drawn here one edge, but of course this happens everywhere on the tree. So let me now return to the discussion of representations and the problem of classifying discrete series representations of p-adic groups. These are the fundamental contributions of Gopal Prasad to so-called supercuspidal representations. So let me remind you, a discrete series representation is one where all matrix coefficients are square integrable functions on the group. Well, it turns out that in the p-adic case, most discrete series representations actually satisfy an even stronger condition. So this is a square integrable or discrete series representation. The stronger condition is that, in fact, the matrix coefficients are compactly supported. Again, if the group has a positive dimensional center, one has to divide by the center for this condition. And these representations are called supercuspidal. And I'm going to focus my discussion on them. The classification of these representations begins with a crucial invariant for any representation introduced by Moy and Prasad. And this invariant is called the depth. What is the depth of a representation? Well, let's consider an irreducible representation. The entire group is not going to fix any non-zero vector in that representation, because if it did, that would mean that this representation contains the trivial representation and it's not irreducible. However, for any point in the Bruhatitz tree, if we consider the corresponding Moy-Prasad filtration, then because this filtration converges to the trivial group, some filtration subgroup is going to fix a non-zero vector in the representation. And the level in the filtration where this occurs is called the depth of the representation at that particular point in the Bruhatitz building. And as we go over different points and take the infimum of all possible depth at those points, we obtain the depth of the representation. So Moy and Prasad proved that this infimum is actually realized at some point in the Bruhatitz building. So this is the concept of depth. And after it was defined, Moy and Prasad obtained the following fundamental result about supercuspidal representations of depth 0. They say that if pi is supercuspidal of depth 0, then it has to arise in a very particular way. Namely, it has to be given by a compact induction of a representation rho of the stabilizer of some point in the building. So let me be a little bit more precise. First of all, I will not say exactly what compact induction is. It's a very standard tool. It's similar to parabolic induction in some ways. But this X here is a point in the building of G, the Prohatitz building, and Moy and Prasad say that in fact it has to be a vertex, not just any point, but a vertex, a polysimplex of smallest dimension. Gx is the associated stabilizer for the action of the group G on the building. And then rho is an irreducible representation of that stabilizer. Now that stabilizer is compact open modulo center, so rho is in fact a finite dimensional representation, but Moy and Prasad say quite a bit more about that. And this involves, again, this filtration, namely, rho has to be not just a representation of g of x, but it has to descend to a representation of the quotient of g of x modulo g of x of 0 plus. Now that group is a finite group of Lie type, and for such groups there is a notion of cuspidal representation. And so Moy and Prasad said it has to be an irreducible representation of this quotient that is cuspidal. Cuspidal here means that as far as the finite group of Lie type is concerned, this representation rho does not arise as parabolic induction from a proper Levi subgroup. Moreover, the pair of X and rho is uniquely determined by pi up to conjugation. So this comes very, very close to classifying supercuspidal representations of depth 0. If one understood the vertices in a building, and if one also understood the cuspidal representations of finite groups of Lie type, and those are very well understood by work of Lustig, at least in the case where the finite group of Lie type is connected, then one understands depth 0 supercuspidal representations. Now, as far as supercuspidal representations of positive depth are concerned, a major step forward in their classification was obtained by Ju-Kang Yu, the collaborator of Gopal Prasad that I mentioned earlier, who gives a construction. So Yu says, given, or maybe I should formulate it in the following way, a positive depth supercuspidal representation of G is obtainable or obtained from a datum. So maybe I should say can be obtained, and you'll see why I want to make this distinction in a moment. So can be obtained from a datum with the following shape. There has to be a tower of connected reductive groups, subgroups of G. For each of them, I'm going to give a character that is a group homomorphism from that group into the group of multiplicative group of complex numbers. And finally, I'm going to give a depth 0 supercuspidal representation of the smallest group in the tower. And there are various technical conditions on this datum that I don't want to go into. But the point is that one can think of this as a construction with an inductive nature, which assumes understanding of depth 0 supercuspidal representations, and from them produces representations of higher depth for G. Now, this result is a little different from the result of Moy and Prasad. It doesn't tell us that if we have a supercuspidal representation of positive depth, it comes about this way. It just gives us a construction of how we can get some of them. So of course, a basic question is, well, how many of them do we get? Do we get all of them? Do we get most of them? And this is a result that was obtained later due to Julie Kim, and then recently strengthened by Jessica Finson, which says that, in fact, we do obtain all of them. So we can say use construction is exhaustive. That is, it exhausts all positive depth supercuspidal representations, provided that P is not too small for the group G. So this was the way Keum phrased her result. There was some very inexplicit bound on P in terms of the group G. The strengthening brought by Finson was that the bound on P became sharp as soon as P does not divide the order of the Weil group. Use construction is exhaustive. Finson also removed the condition that was present in Keum's result that the characteristic of the field had to be 0. Now, what happens if P divides the order of the Weil group? Well, we know that there are supercuspidal representations that are not obtainable from use construction. So for those P, the classification of supercuspidal representation is still open. But at least when P does not divide the order of the Weil group, we don't have a classification per se, but we have a construction that produces all representations. Now, the next step towards classifying them was obtained by Hakim and Moynihan, which I'm not going to say precisely the theorem. I'll just say that they introduce an equivalence relation on U data, and then they prove that the representations are isomorphic if and only if the data that they are produced from are equivalent with respect to this equivalence relation. And of course, the strength of the theorem is the fact that the equivalence relation is very explicit. Now, all of these theorems, use theorem about the construction, the Keum and Finson result about exhaustion, and the Hakim-Moynihan result about the equivalence relation, they all fundamentally rest on the innovations that Moy and Prasad, and also Prasad and Yu, brought into the theory of representations and structure of p-adic groups. The Moy-Prasad filtrations, the notion of depth, the Moy-Prasad isomorphism, as well as the actions of finite groups on buildings and tame descent for buildings. All of these things are crucially used in all of these results. Now, let me tell you a little bit about another side of the story, and that is the concept of Harish-Chandra characters. So let's think again first to the situation of which is simple, namely we have a finite dimensional representation. So if the dimension of V is finite, then a very basic construction in representation theory assigns to this representation a function on the group called its character. And what it does is it simply takes the trace of the matrix associated to the group element G. This is a finite dimensional matrix, so it has a trace. And this function captures all the information of the representation. Two representations are isomorphic if and only if they have the same character. Now, in the setting that we find ourselves in, the dimension of V is almost always infinite, so this simple construction doesn't work. But it was a cornerstone of Harish-Chandra's theory that one can actually define a function not on the entire group, but on the so-called regular elements, which is an open dense set in the group. And this function behaves in very similar ways to a character, and in fact, it captures the essence of a trace function. And it is a curious bit in the classification, in particular of discrete series due to Harish-Chandra, that in fact this function was used to classify discrete series representations or square integrable representations without those representations actually having been constructed. So Harish-Chandra gives over the real numbers, Harish-Chandra gives formulas for chi-p, in particular for discrete series representations. And the way this was done is Harish-Chandra studied abstractly what properties this function would have if it was associated to a discrete series representation. And he found that this function has to satisfy certain differential equations that are so strict that they basically completely determine the function. And using this, he was able to classify the discrete series representations before they were constructed. They were later constructed in the work of various authors, in particular in the work of Schmidt, following a conjecture of Langland's. On the other hand, over QP, the development was opposite. First, the representations were constructed in the work of Yu, and then formulas for their Harish-Chandra characters were given. And here, the formulas I'm talking about come from the work of De Backer and Reeder for supercuspidal representations of depth 0, and Adler and Spice, Adler and Spice for positive depth supercuspidal representations. So they give formulas for chi-p. Again, these formulas use in a very significant way the concepts of a Moy-Prasad filtration and a Moy-Prasad isomorphism to obtain these formulas. And now let me circle back to the Lefschetz principle, from which we seem to have strayed away quite a bit. So in the beginning of this talk, I discussed how one classifies admissible representations in terms of temperate representations by the Langland's classification, and how one classifies temperate representations in terms of discrete series or square integrable representation via Harish-Chandra's theory of R group. And I discussed that those results are valid in the same way over the real numbers and over the p-adic numbers. And the Lefschetz principle was the hope that other classification results will also be analogous for real and p-adic groups. But then we strayed away quite a bit from this principle by studying the fine properties of p-adic groups, contrasting them to the fine properties of real groups, and seeing how, first of all, there are these representations of p-adic groups called supercuspidal that don't even have an analog for real groups. And secondly, the construction of representations for p-adic groups is especially supercuspidal representations, is very different from that for real groups. However, it turns out, rather surprisingly, that the Lefschetz principle still holds even for discrete series. So to try and convince you of that, let me finally say what the Harish-Chandra classification of discrete series representations for real groups is. So Harish-Chandra classifies discrete series as follows. So over the real numbers, the group G has square integrable representations if and only if G has an elliptic maximal torus. Now, if G has an elliptic maximal torus, it turns out to be unique up to conjugation. So let's fix it for a second. And then discrete series representations are classified in the following way by pairs, where theta is a character of that fixed torus, and B is a Borel subgroup with respect to which the differential of this character is dominant. And then one takes orbits under the Weil group, and Harish-Chandra says that this parameterizes discrete series representations. Well, on the other hand, we saw that supercuspidal representations are parameterized by these very unwieldy looking U data, so they look very different. But let us now do something. Let us restrict attention from all discrete series to, in some sense, a large open subset of them, if you will. What do I mean by this? This Borel subgroup is going to give us a cone, and the differential of this character theta is supposed to be in this cone, and it could possibly be on the wall of the cone. So what I propose is, let us ignore the situations where the differential is on the wall of the cone and just consider only the inside of the cone. And let us call the corresponding discrete series representations regular. Well, if it's inside the cone, then this Borel subgroup becomes superfluous. It is determined by the point. And so what we can do is we can, first of all, remove it from consideration, but then secondly, introduce the torus S, which was unique up to conjugation. And so what we now have is G of R conjugacy classes of pairs of torus and a character. The torus is an elliptic maximal torus, and the character has regular differential. And again, Harish Chandra is going to tell us that this now corresponds to what we call regular discrete series representations. Okay. Moreover, Harish Chandra is going to give us a formula for the character. In particular, if we take an element in that very particular torus, then Harish Chandra gives us a formula for this character function, which has a fairly simple nature. First of all, there is a plus minus sign in front, then there is a sum over the vowel group, and inside we have the character evaluated at an element S moved by the vowel group, divided by what is called a vowel discriminant. So this is the formula. Now, what about over the p-adic numbers? Well, using all the results that I mentioned previously, the results of U, of Hakim Moynihan, of Keum and Finson, as well as the results of Moy and Prasad and their techniques, I was able to prove the following theorem, that first of all, there is a concept of a regular supercuspidal representation. In fact, I can tell you what it means in terms of the U datum here. It's only a condition on this pi minus 1, which in turn, by Moy-Prasad theory, corresponds to a cuspidal representation of a finite group of Lie type. And for those, there is a Deligne-Lustig theory. And we require that this cuspidal representation comes from a regular Deligne-Lustig induction, which is the case for most, but certainly not all supercuspidal representations. So in some sense, the mental picture should be similar to this, that we are omitting certain singular components, but most of the things are regular and we're considering them. It turns out that they're in bijection, which this again pairs of a torus and a character, up to conjugation by GQP, where S is an elliptic maximal torus, which is tame, and theta is a regular character of that elliptic maximal torus. Now, regularity is not defined in terms of a differential because there is no differential, but there is another way to define regularity. And again, we have a bijection like this. So the classification of discrete series for real and p-adic groups actually turns out to be formally exactly the same, provided one restricts to these big open subsets of regular representations. And then there is also a theorem about the Harish-Chandra character. Namely, if we take an element in this torus, which is shallow is in terms of the Moy-Prasad filtration of the torus, then the character formula evaluated at this element has a certain shape. Let me write it down first. Now, there are various bits in that formula, and I don't want to go into the discussion of all these bits. I'll just tell you what the punchline is. The punchline is that all of these various bits, this is a plus minus sign, this is a root number of a certain Galois representation, this is an explicitly defined function, this is the character theta. All of these have a natural interpretation both over the p-adic numbers and over the real numbers. And over the real numbers, the interpretation makes this function or this formula be exactly the same as this formula. So in other words, not only is the classification of regular discrete series representations for real and p-adic groups the same, but also their Harish-Chandra character on these key elements of the torus is described by the same formula. So from that point of view, one sees that the Letschert principle also holds among the discrete series representations of real and p-adic groups. Again, not only the proofs, but even the statement of this theorem is completely dependent on the contributions of Gopal Prasad and his co-authors to the structure and representation theory of p-adic groups, as one sees, for example, by this word shallow here. So with this, I would like to end this talk, and even though it is a day early, I would like to wish Gopal a very happy birthday and to congratulate him on his wonderful achievements in the theory of p-adic groups. Thank you.